So get this, the estimated physical production cost of the iPhone X, just $412.75. I mean, think about that for a second. The exact same phone that millions of people held in their hands, literally packed with groundbreaking tech, like that super crisp Samsung-made 5.8-inch display, it only cost around $400 to physically create. But here's the kicker. When it actually hit the shelves, that base 64-gigabyte model started at $999. That is a massive 59% difference. Okay, so let's really dive into this. How on earth does a massive company like Apple come up with these estimates before they ever put a price tag on a product? How do they balance, making this incredibly advanced piece of tech with making sure they actually turn a profit? That mystery right there, that gap between what it costs to make something and what it's ultimately worth to the business, that is exactly what we are unpacking today. Welcome to this explainer, where we're diving into the introduction to engineering economy. You can kind of think of our journey today as building a giant bridge, right? On one side, you have the island of pure engineering innovation, the brilliant designs, the crazy new tech, the bold ideas. But over on the other side, you've got the island of profitability and long-term business survival. Engineering economy, well, it's the absolute critical bridge that connects those two islands together. Here is a quick look at our roadmap. We'll look at engineering meeting the bottom line, compare accounting versus engineering economy, walk through the rational decision-making process, hit the 7 principles of economy, and wrap up with cost-driven design optimization. Basically, we're going to learn how to evaluate benefits over costs, just like the top tech companies do. Okay, first up, Section 1, Engineering meets the bottom line. Let's look at how we actually translate innovation into cold, hard profit. Let's start with a hard truth that pretty much every designer and engineer eventually has to face. An engineering solution, no matter how creative or technologically mind-blowing it is, absolutely must translate profitability to the bottom line. If a project doesn't help the organization financially survive, well, it's honestly just a really expensive science experiment. Take the Boeing 787 Dreamliner, for example. It brilliantly illustrates this whole journey. The engineers don't just design the physical plane, pat themselves on the back, and call it a day. No way. Their role goes deep into the business side. They're analyzing production methods, looking at market assessments, checking environmental impacts, and from there they have to evaluate expected profitability, exactly when cash flows are going to hit, and the financial risks involved. Literally every single technical decision they make impacts the firm's financial statements, its stock price, the whole shebang. And to bring these abstract ideas down to earth a bit, economic analysis plays a massive role in practical, everyday situations. It's the math behind choosing the absolute best design for a high-efficiency gas furnace. It's figuring out exactly which robotic arm to buy for a welding operation on a car assembly line. It's making the huge call on whether an overnight delivery service should buy or just lease their fleet of cargo jets. Honestly, it even applies to figuring out the most cost-effective way to staff a computer help desk. At the end of the day, every technical choice is fundamentally a financial choice. Moving right along to Section 2, Accounting versus Engineering Economy, we're shifting gears from looking at past records to predicting future events. Now, this requires a little bit of a paradigm shift. If everything is tied to money, how do we actually track all these costs and revenues within a company? Look at the clear contrast here. On the accounting side, it's all about evaluating past performance. It's strictly looking in the rearview mirror at the records of what has already happened. But engineering economy, it is entirely focused on evaluating and predicting future events. We aren't looking in the rearview mirror anymore. We are staring straight out through the windshield. And because we're predicting the future, time and uncertainty become the defining aspects of literally every decision we make. We have to estimate the required investment before a project even gets off the ground. We're forecasting product demand before the product even exists in the real world. We're guessing selling prices, manufacturing costs, and trying to figure out how long a product will actually survive in the market. It's basically this massive, complex puzzle of future variables where absolutely nothing is guaranteed. Which brings us to Section 3, Rational Decision-Making Process. Let's see how engineers logically navigate all that crazy uncertainty. So, this is the step-by-step playbook engineers use to rationally solve this mystery of profitability. Now, a full analysis actually involves 7 steps, but let's just focus on the 4 critical early phases right here. First, problem definition. You've got to know exactly what goal you're trying to achieve, right? Second, the development of feasible alternatives. Because let's face it, there is never just one way to engineer a solution. Third, you develop the prospective outcomes and cash flows for every single one of those alternatives. And fourth, the selection of a decision criterion. Basically, what specific rule or metric are we actually using to pick the winner? Let's look at the numbers side by side to really ground this. Say you need a vehicle for your business. We are intentionally isolating the financial differences between our options. You wouldn't just guess, right? You'd map it out. The monthly fuel costs, the maintenance, the cash outlay at signing, and the salvage value down the road at year 3. The whole point of this exercise is to make sure we are comparing apples to apples based entirely on the financial impact. Pointing back to our source example, let's say we're choosing between 2 car models, a Beza and a Saga. We've recognized the problem, we need a reliable car, we've gathered all the technical and financial data. Now, if our selected decision criterion is specifically to get the minimum total cash outlay, well, the logic dictates we go with the Saga. Doing it this way takes all the guesswork and emotion out of the equation and aligns perfectly with our stated financial goal.
All right, Section 4, 7 Principles of Economy. Think of these as our absolute golden rules.
To consistently make rational choices like that car example, and to prevent brilliant engineers from making terrible financial mistakes, we have 7 fundamental principles. Ready? Develop alternatives. Focus exclusively on the differences between them. Use a consistent viewpoint. Use a common unit of measure. Consider all relevant criteria. Make uncertainty explicit. And finally, always be ready to revisit your decisions. Now, I really want to emphasize using a common unit of measure, which is almost always money. This is absolutely crucial because it's the only way to ensure that drastically different alternatives, say comparing a hybrid car to a hydrogen car, are actually evaluated fairly on the exact same basis. Finally, Section 5, Cost-Driven Design Optimization. This is where we bring it all together to maximize profitability. Let's see how all this builds into a practical workflow. This is it, the ultimate bridge between engineering and business, where you actively design a product to maximize profit right from day one. Optimizing a design for cost is a clean 4-step process. Step 1, identify the design variable that acts as your primary cost driver. Step 2, express your cost model mathematically based on that variable. Step 3, if it's a continuous function, you differentiate it using calculus to find the optimal value. And step 4, simply solve the equation to pinpoint the absolute minimum cost value. Easy enough, right? So the really crucial point here is perfectly captured in this simplified cost function. Total cost equals A times X plus B divided by X plus K. Okay, what does that mean? X is our primary design variable. A represents directly varying costs, stuff that goes up as X goes up. B represents indirectly varying costs. And K? Well, those are your fixed costs that stay exactly the same no matter what. By intelligently tweaking that X, an engineer isn't just designing a functional part. They are mathematically pinpointing the exact design that minimizes total cost for the whole company. It's kind of brilliant. We started today by looking at the incredible technology and the shockingly low production costs of an iPhone X. And we've seen throughout this explainer that engineering isn't just about what is technically possible, it is fundamentally about what is financially viable for an organization to survive. So I'm going to leave you with this final provocative thought to chew on. If your next engineering project is an absolute technical masterpiece, but it turns out to be a complete financial failure, did you really solve the problem? Keep that in mind the next time you evaluate a design. Thanks for learning with me today.